Hi.
I'll wait, just, yeah, okay, fine. Yeah, now I can introduce you and we can go ahead.
Okay.
Okay. First, let me, yeah, it's fine. Okay, hello everyone. Welcome to the 43rd meeting of New Directions in Group 3 and Triangulated categories. Today, we are very pleased to have Hans-Werner Henn from the University of Strasbourg, and he will be speaking to us about the Brown Comenetz dual of the K2 local sphere at the prime 2. Please go
ahead.
Hans-Werner.
Okay. Thanks for the introduction. Thanks for the invitation to talk. So this is the title you see on the screen now, on the Brown Comenetz dual of the K2 local sphere at the prime 2. And this is joint work in progress with Paul Goerss, who is visiting here at the moment, and whose help was needed earlier this afternoon to get me familiarized with my iPad. And he stepped in at the moment also, so some technical problems. Well, okay. So, I mean, I see who's, I guess the people who are here sort of know this background material pretty well. So, but there are a few names I don't know. So I will recall some of the things which are sort of very well known to probably most of us, most of you. So Brown Comenetz duality is something which happens in chromatic homotopy theory. So some background on chromatic homotopy theory, we fix a prime P, and then the height filtration of the moduli stack of one-dimensional formal group laws over P local rings has a counterpart in the category of P local spectra, known as the chromatic filtration. And so in this game, important spectra. So Kn is the nth Morava K theory spectrum. So Kn star is, well, depends on how you define it. It's whether it's defined over C mod P or over an extension. You can define it over C mod P, and it's a periodic theory on the generator Vn, whose degree is 2 times P to the n minus 1. K0 is by convention, it's not Q, it should be HQ. So let's see, so I have my pencils somewhere. It's hiding. Here it is. Just in order to
you actually wrote K0 star, so it should be okay to call it Q.
So it's HQ. So I think it's probably not worth sort of our time to make me activate my pencil and fix this typo. So LKN is then Bowers-Filter localization with respect to Kn star, and Ln is Bowers-Filter localization with respect to the wedge of all the Km's from M running from 0 to n. So examples are L0 is rationalization, LK1 is localization with respect to mod PK theory, and L1 is localization with respect to P local K theory. Well, these functors, Ln, they assemble into a tower known as the chromatic tower. Chromatic homotopy theory is the study of the P local stable category via the tower of Bowers-Filter localization functors Ln. So this is displayed here. And then there are 2 important things one needs to know about this tower. Well, there's chromatic convergence says that for finite P local spectra, the right-hand tower is pro-isomorphic to the constant left-hand tower. And Ln is determined by Ln minus 1 and Lkn. And more precisely, for every x, there's a homotopy Pullback square, which I like to call, well, which I think it's often called the chromatic square. So Ln of x is determined by this Pullback square by Lkn, Ln minus 1, and Ln minus 1 of Lkn. And the categories Kn of Kn local spectra are the basic building blocks of the category of P local spectra. That's another typo. Well, the category Kn is symmetric monoidal, this mesh product given by the usual mesh product, but that is not Kn local, so you localize again. And the unit for this monoidal category is LKN of this field. Well, this smash product defines then the structure of an abelian group on isomorphism classes of spectra, of K in local spectra, which has been introduced by Hopkins in the late 1980s. And this will be denoted by pic and P, or if P is understood from the context, just by pic n. Well, this group is a profinite abelian group, and in fact, there's a natural filtration on it, so or natural topology on it, which is given by certain finite index subgroups. I mean, every small object in Kn defines a finite index subgroup, not only a set, a finite index subgroup, I think. That's just those Y in Pic which become. There's another typo. It's those Y in Pic which become. Oops, I'm confused. What should I read it here? We should read F smash Y is equivalent to F. Okay. So here, this place. Oops, wait a second. I'm not quite sure. See on the other screen what you see. What you're seeing at this place. It should say smash equivalent to F. Now, if X is in Pic n, or X is in Pic n, if and only if K star of X is equal to K star up to suspension, and there's an associated homomorphism from Pic n to the cyclic group of order degree of Vn, and the kernel of that map is a pro-P group of index 2 times P to the n minus 1. Well, there's an algebraic approximation of this Picard group. So if you have a K in local spectrum X, then you can look at its Morava module. So that's given by pi star of En smash Kn of X, and En is Morava E theory. That's given by a certain E infinity spectrum whose homotopy groups are given by this isomorphism. It's a non-canonical isomorphism. W is the WFPN is the Witt vectors over the finite field Fp to the n. The Ui are of degree 0, and the U, which is of degree -2, should not have any index. Well, the ring pi0 of En classifies deformations of a suitably chosen formal group law gamma n of height n over the field Fp to the n, and the automorphism group Gn of the formal group law acts on pi0 En, and by Hopkins Miller-Goerss even on the E infinity spectrum En, and hence on the Morava module. The group Gn is a compact p-adic Lie group known in homotopy theory as the Morava stabilized group. The basic example is given by, it's the case n equals 1. The case n equals 0 is sort of exceptional and trivial. The case n equals 1, we have pi star of E1, that's just p-adic complex K theory. So its coefficients are given by, that's not a power series ring, it's a, well, it's a graded power series ring, so the graded power series ring, the graded polynomial ring are the same, but I mean, these double brackets are sort of also a typo. The group G1 in that case identifies with the units in the ring of p-adic integers, and the action of G1 on E1 is via Adams operations. Okay, so the algebraic Picard group is given in terms of the symmetric monoidal structure of the category of Morava modules, whose tensor product is just the tensor product over pi0 of En. It's a completed tensor product. I think I should. So this gives rise to a homomorphism from Pic n to the algebraic Picard group. And in fact, well, I think I can actually skip the next page. Well, okay, so yeah, I'm not going to talk much about the Picard group. So this is a file which is partly recycled from a talk I gave last year. And that, I think I can actually skip this page. Okay, so let's get to Brown Comenetz duality. Brown Comenetz duality is a functor from K in local spectra to a K in local spectra. Well, Brown Comenetz duality is actually a more general thing, but I should probably say Gross-Hopkins duality. Is a functor from K in local spectra to K in local spectra, which is closely related to Pontryagin duality. In particular, if X is a spectrum of type N, then pi 0 of In of X is just the Pontryagin dual of pi 0 of Lkn of X. The spectrum In of Lkn of S0 will be simply denoted by In. This is an element in Pic N, and the Gross-Hopkins formula identifies it within the algebraic Picard group by an isomorphism of Morava modules. That means I star of En is isomorphic to E star of In is isomorphic to E star of Sn squared minus n twisted by the determinant. So the determinant is a certain homomorphism from Gn into the p-adix. And so that actually is given, if you want, by E star of Sn squared n tensor C2 twisted by the determinant. Huh? I mean, so this homomorphism makes the p-adix, I should say. Into Morava module. So I realized, in fact, I do have to go back to the last slide because, well, I could actually go to this slide. The kernel of this homomorphism is denoted kappa n. And I can actually skip this. Okay, so one could say that the Gross-Hopkins formula determines In modulo this subgroup kappa n, which is the kernel of the Picard group, of the homomorphism from the Picard group to the algebraic Picard group. The homomorphism, of course, is given by sending X to En0 of X, as it's indicated on this previous slide. Okay. So let's look at the simplest case, the case n equals 1. Well, if P is odd, then kappa 1 is 0, and the Gross-Hopkins formula determines the homotopy type of In. If P is equal to 2, then kappa 1 is equal to sigma 2. And the question comes up what that really means. Well, independent of an answer to this question, it turns out that I1 is the K1 localization of a certain finite complex, which is usually denoted or called the question mark, the dual of the question mark complex. So it's a 3-cell complex whose Steenholt modular structure is given by that. There's something in degree 0, 1, and 2. So that's H star of dq. And so that's actually obtained from by attaching a copy of the suspension of the Moore space to S0 via a map, which is the Hopf map on the bottom cell. At odd primes, it's not very hard to produce natural models of SDAT. In fact, it's enough to specify a homotopy action of the p-adix, a unit in the p-adix on the p-completed sphere. And then, well, and I might come back to a more precise description of the construction, but in fact, I mean, we've understood S-stat at odd primes. I mean, how to construct S-stat at odd primes for a while. That's the prime 2 is more subtle. And in fact, at the prime 2, there are sort of two natural candidates for an action. So I'm not going to make very precise what I mean by an action. It's a genuine action restricted to the subgroup, the finite subgroup of the units in the two-adics. And you can think of it as a homotopy action on the complementary copy, which is given by 1 + 4 times C2, which is via a logarithm isomorphic to the additive group of the two-adics. And so it's just given by, so for the action of ±1, you consider the virtual representation sigma -1 and 1 - sigma, where sigma is a sign representation of the group of order 2. And then accurate and stable homotopy gives us spectra S sigma -1 and S1 - sigma, which arise from the 1-point compactifications of corresponding representation spheres. And then the homotopy action of the complementary factor C2 is given by choosing a homotopy equivalence of degree 5 on either S sigma -1 and S1 - sigma. And then the fiber of this homotopy equivalence are denoted S plus and -1. So in a paper by Pontryagin, Bartels, Goerss, and Stoyanowska, they actually consider it as sigma -1, and they call that the Tate sphere. But in fact, there are two versions of the Tate sphere. Let's call them S plus, respectively S -1. And then one can define S plus or minus that as taking the Morava EN theory spectrum, smash it with this version of the Tate sphere, and take homotopy fixed bounds with respect to Gn. And at odd primes, you can make sense out of these homotopy fixed points, even though you only need to specify a homotopy action of Gn on, I mean, to construct the Tate spheres, well, there's only one, the Tate sphere at an odd prime, it's enough to specify a homotopy action. I mean, the basic fact is the finite subgroup of the units in the p-adics for p odd is of, I mean, the finite subgroup is of order prime to p. Okay, so what's known for kappa 2 and Brown Comenetz duality for odd primes? I have to watch a little bit the time. I've started probably 5 minutes late, so I think I'm doing fine. If p is bigger than 3, then kappa 2 is 0 again, and therefore the Brown Comenetz dual I2 is given just by S2 smash S-stat by the Goerss-Hopkins formula. If p is equal to 3, then kappa 2 is C mod 3 cos C mod 3. That's something like Paul and me proved or published several years ago, maybe 6 by now. And in fact, there's a unique p in kappa 2. I mean, one can take that as definition of p, which satisfies I2 smash S is equivalent to S2 smash S-stat smash p. And one would like to identify this p within this group C mod 3 cos C mod 3. And in fact, I mean, I won't go into the detail because that's not really the new work, but this p can be characterized by the property that if you take the smash product with V1, with a Toda-Smith complex V1, then you get the 48-fold suspension of LK2 of V1. And that specifies it in one of the two C mod 3 factors, and the other factor is not even involved. Huh? So the challenge that we have now is what happens for p equals to 2. And that's related, of course, to first identifying what is kappa 2. So the next few slides are on the collaboration of Paul Goerss, Pham, Stoyanovska, and myself. And so we actually have a document by now, but it's still not really ready to be released. But it's a long-term project that we've been engaged into. And I think, we have proofs, but we are not yet happy with our presentation. So in order to describe kappa 2, I need to say a little bit more about G2 at the prime 2. So it can be understood in terms of a super singular elliptic curve, which is defined over F4 and can be given by it's given by the explicit formula y squared plus y equals x cubed. Then this E is super singular. That means the formal group law gamma induced by the group structure near the point at infinity, or at the point infinity, is of height 2. And G2 is the automorphism group of this formal group. The automorphisms of the elliptic curve itself is isomorphic to GL2 of C3, and it injects into G2 as the up to conjugate a unique maximal subgroup. It's often denoted by G48. GL2 CMO3 is certainly a better name. Automorphisms of E is maybe the most appropriate name. Well, so as I said before, there is this determinant homomorphism from D2 from the there's a determinant homomorphism from a certain division algebra from the units in a certain division algebra to the units in the two-adics, in the field of two-adic numbers. And this induces a homomorphism from G2 to C2. The units in C2, that's in fact the determinant that I've been talking about briefly before. And then we can compose that with a canonical quotient map where you divide out by the finite order, the subgroup generated by plus and minus 1 in the units of the two-adics. And the kernel of that map is called G21. So the group kappa 2 admits various filtrations. So the first filtration, which I also will call later on the subgroup filtration, well, that relies on the following observation. Well, if H is a closed subgroup, well, first of all, we define for every closed subgroup, we define kappa 2 of H. So that's those isomorphism classes in kappa 2 which become standard, for which E2H, the homotopy fixed points of E2 with respect to H smashed with X become equivalent to E2 HH. Well, I guess the notation is very badly chosen for a talk where you have to pronounce HH and one H is capitalized and the other one isn't. Well, it's obvious that if H, there's a warning for large chromatic level, one could try to give a similar definition, but in the process of writing this paper, we discovered that things can become subtle. And so there's just a warning for chromatic level, for large chromatic level, this definition may have to be refined. Well, should be refined. Well, the obvious observation is if H1 is a closed subgroup of H2, then kappa 2 of H2 is contained in kappa 2 of H1. Okay. In particular, kappa of G2 is contained in kappa of G21, is contained in kappa of G48, which is contained in kappa of the trivial subgroup. And kappa of G2, by definition, is the trivial subgroup of kappa, and kappa of 1 is kappa itself. So in this collaboration, we actually study kappa 2. We identify kappa 2, but so I'm going to present the result the next slide, or maybe the slide even after the next. So let me first sort of say something about this filtration. At the bottom of the filtration, kappa G21 is isomorphic to C mod 8 cross C mod 2 squared. The next filtration quotient is isomorphic to C mod 2, and the top filtration quotient is isomorphic to C mod 8. Oops. Well, there's a second filtration of kappa 2, which is given in terms of the sense spectral sequence. And so if X is in kappa 2, then the sense spectral sequence has the same E2 term as the K2 local sphere. And in particular, there's a fundamental class in E200 of X. And the fundamental class for LK2 of S0 is a permanent cycle, which detects the unit in pi 0 of LK2 of S0. Now, the second filtration, also called the Adams-Novikov filtration, can be defined as follows. If R is bigger than 2, then we let kappa 2 of R be the, in fact, it turns out to be a subgroup of isomorphism classes of elements in kappa 2, or subgroups of spectra, invertible spectra, such that IX survives to the R term of the Adams-Novikov spectral sequence. And then it's clear that if R1 is less or equal than R2, then you get inclusions kappa 2 R2 in kappa 2 R1. And in fact, you have because the only differentials you can have are odd differentials, and you have a decreasing filtration. Kappa 2.7 is in kappa 2.5, it's in kappa 2.3, is in kappa 2, and in fact kappa 2.9 is equal to 0. And the second filtration actually is you have kappa 2.7 is C mod 2 cross C mod 2. The next filtration quotient is C mod 4 cross C mod 4 cross C mod 2. And the top filtration quotient is C mod 2 cross C mod 2. And playing out the two filtrations against each other gives that the first filtration of kappa 2 is completely split. That means kappa 2 is isomorphic to C mod 8 cross C mod 8 cross 3 copies of C mod 2. The filtration is completely split, but we don't have a canonical isomorphism, which is painful a bit. But nevertheless, we understand the structure of this group. It's a group of order 2 to the 9. So it's a huge group. I mean, it's not very complicated as an abelian group, but if you don't have an explicit isomorphism, it may be very difficult to locate an element in this group. So the remaining challenge is we have two versions of the determinant. Both of them are, I mean, sort of have the right Morava module. And so they differ by an element in kappa. And P plus and minus are also elements in kappa, and they are uniquely characterized by this equivalence. I2 should be equivalent to S2 smash S plus or minus that smash P plus or minus. So the challenge is to find a characterization of pi plus minus. Well, the idea is to try to use chromatic splitting to get more information on P plus minus. I should warn you, if you have, I mean, well, the title sort of suggests, the title of the talk suggests that we don't sort of succeed in locating P plus minus completely, but we do get more information. And in fact, we use chromatic splitting to get more information. So chromatic splitting, that's a paper which was published recently. And the main theorem in this paper, well, one of the main theorems in this paper is The Fête de la Musique starts today in Strasbourg, so I have to close my window. And the window, closing the window is a noisy process, as you noticed. So, so in this collaboration, we proved that LK1 of LK2 as 0 is in fact LK1 of a finite complex, which is given by SO, or finite spectra, which is given by SO, which has -1, which the -2-fold suspension of the Moore space, and the -3-fold suspension of the Moore space. So that's not an easy theorem. I mean, it takes a lot of work. There's a consequence of this theorem, which is comparatively easy. We can sort of use that to get information about LK1 of I2. And in fact, there's an equivalence. LK1 of I2 is LK1 of another finite complex. And now this dual question mark complex shows up. We have the 4-fold suspension, which the 3-fold suspension of the dual question mark complex, which the suspension of VSO, which VSO. So, I mean, I was sort of speculating for, I think, more than probably at least 2 years, that S det would be just, if the K1 localization of S det would be just sort of desuspending that guy on the right-hand side by sigma 2. But I was very naive at the moment. At the beginning, I didn't know that. I mean, maybe I was speculating about that already in 2019. But I was very naive at the beginning, and I didn't realize that there's a real difference between S plus det and S minus det. I mean, we'll actually we'll get to that in a moment. Now, sort of in the last 2.5 months, Paul and me have sort of tried to, well, I think we have succeeded actually to prove that for S minus det. There exists an equivalence LK1 of S minus det, which is just equivalent to LK1 of sigma minus 2 of I2. LK1 of S plus det has a more complicated homotopy type. In fact, there is a unique Q in kappa 2 such that S plus det is equivalent to S minus det smash Q. And this Q is a well understood lift of the non-trivial element in kappa G48 divided by kappa G21, which was isomorphic to sigma 2. That was sort of the middle filtration quotient in the subgroup filtration. And the Q is actually given by, you take E2 smash the spectrum S2 sigma minus 2, you take as the representations for S2 sigma minus 2, there's a map from G2, there's a homomorphism from G2, and then you divide out by 1 plus 4C2, so that's the sigma 2, and you take here the smash product E2 smash S2 sigma minus 2 with a diagonal action of G2, and you take the homotopy fixed points. So we can say something about the homotopy type of half of LK1 of S det. I mean, like LK1 of LK2 of S0 is sort of sits in a vibration where you have of a self map of LK1 of EHG21 homotopy fixed points with respect to the subgroup G21. A similar thing is true for LK1 of S plus and S minus det, and we do understand LK1 of half of S minus det. I mean, that's sort of the language that Mark Mohwald would have used. Well, so how well do we understand P plus? So So we have LK1 of S minus that. We have that very well under control. And the hope was that this would tell us something about the spectrum P plus or P minus. Okay? Well, the image of P plus in the top filtration quotient of the subgroup filtration has been understood for a while. In fact, I mean, Morava predicted maybe more than 10 years ago that P plus and P minus, well, they were not around at the time, but, well, no, I'm sorry. There were no, SDET was not really around at the time, but he predicted that this correction term, think of P plus, P minus, as a correction term for the Brown Comenetz formula, it should have the property that it maps to a generator of kappa modulo kappa G48, which is isomorphic to C mod 8. And in fact, I mean, this isomorphism, there's an explicit isomorphism, which is given as follows. If kappa is in kappa 2, one can show that there's an integer k, which is unique modulo 8, such that if you take E2HG48, the homotopy fixed points with respect to this maximal finite subgroup, smash X, then you get a 24k-fold suspension of E2HG48. And in fact, we know enough by now to say what happens for P plus and P minus. In fact, P plus and P minus, they differ by something which is in G48. So they will have the same image in this quotient group kappa modulo kappa G48. And depending, I mean, you get a homomorphism to C mod 8, you can associate to X this number K or this number minus K, if you, I think we will take. So let's see. So the map. That we will choose in the sequel will send X to minus K of X. So with respect to that isomorphism, P plus and P minus will be sent to the class of 1 modulo 8. Now the equivalence for LK1 of S minus that and knowledge of Q, so the Q is the thing which differs, which makes the difference between S plus that and S minus that. So that determines P plus minus modulo the subgroup kappa G21, which is isomorphic to C mod 8 cross C mod 2 cross C mod 2. But in fact, I believe we know them even modulo C mod 8. I say believe because this is an idea which occurred to me yesterday when preparing this talk. I did discuss it with Paul. It seems to stand up, but sort of, I mean, this is certainly not documented yet. I mean, not even in rough form. Well, in fact, to say that we know this P plus minus modulo C mod 8, that requires an explicit isomorphism between these two groups. Okay? I mean, there's no canonical isomorphism between these two groups. And in fact, but there is, I claim there is a canonical isomorphism. And with respect, well, okay, so, and that depends on a further filtration of kappa G21. So kappa G21, that's are the spectra which become equivalent after extending to E2H G21, the homotopy fixed points with respect to this subgroup. Now the isomorphism arises as follows. If we consider the group of units in Paiso of the homotopy fixed points of G21. this group admits a filtration which arises from the topological duality spectral sequence due to Goerss. I'm not going to go into the details of that, but there's just a certain filtration of length 3, and it arises from another spectral sequence which has been useful in the project with Agnes and with Paul. So in this filtration, the subgroup F3 is isomorphic to C mod 8, and the two filtration quotients F1 modulo F2 and F2 modulo 3 are both isomorphic to C mod 2. The top quotient is isomorphic to C2, and the filtration is split. And the residual action of G2 modulo G21, which is isomorphic to this the additive group of C2, on this group of units is trivial. And then there's an explicit isomorphism from H1 G2 modulo G21 acting on F1 with kappa G21. Okay, I mean, and then you calculate the left-hand side, and the left-hand side is isomorphic to C mod 8 cross C mod 2 cross C mod 2. But now the filtration of F1 given by the topological duality spectral sequence gives rise to a filtration of kappa G21 with Fi of kappa G21 being given by the first cohomology of G2 modulo G21 with coefficients in Fi for I equals 1, 2, and 3. And I believe we have identified P plus minus as elements in the quotient group kappa 2 modulo F through kappa G21, which is C mod 8 and which is isomorphic to C mod 8 plus C mod 2 cubed. And in fact, there's an explicitly known isomorphism with respect to which P plus has coordinates 1, 0, 0, 0, and P minus has coordinates 1, 1, 0, 0. Well, for going further, we would need to better understand the passage from E2HG21 to E2HG2, the homotopy fixed points with respect to the full Morava stabilized group, which is equal to the K2 local sphere. So that means you would have to understand the centralized resolution better, or we would have to understand the hybrid resolution better that Agnes and me sort of have ideas about. And we would need to know the maps in this resolution better. And I'm not very optimistic that this will be done anytime very soon. Okay, thank you for your attention.
Thank you, Hans-Werner. Can we all unmute ourselves? Yeah, right. Give the speaker round of applause. Yeah, if you have any questions, please ask them now.
Fantastic.
Did I see a raised hand? Okay, let me ask something myself. Hans-Werner, can you go back to that part where you said that this was something you discussed with Paul yesterday, and you are it's still not in written form? Can you expand on that a little bit? If you want to, obviously.
Let's see. So that's. I'm not quite sure which slide you're referring to. Are you referring to that slide, or? Well, I think you must refer to a slide where I say something I believe. Huh?
Yeah, you said you discussed it.
So
yeah.
Maybe this one. Okay.
Yeah.
Okay. So the element which, if you take S minus that, then its K1 localization differs from the K1 localization of I2 just by a double suspension. Okay? And that means and in fact, the element which is in kappa, which is in the middle filtration quotient of the subgroup filtration, is not involved, because that's involved actually in S plus of that, which has this more complicated homotopy type. So the subgroup filtration is further up. It's here, so it's not, this element is not involved in P plus. And the top filtration quotient is, we know what P plus gives in the top filtration quotient. It gives this generator, which, if we take the right isomorphism, corresponds to the element 1. And so a priori we have an uncertainty about modulo kappa T2 1. But in fact, that we know more. I mean, the fact that LK1 of S minus that is up to suspension, just LK1 of I2, that contains more information about P plus. It essentially contains the information which sits in this finite subgroup, which sits in the subgroup C mod 2 cubed, which is a unique subgroup because no, it's not a unique. I'm sorry, it's not unique, but no, I'm sorry, I'm taking that back. But it gives information about what happens in the other 2 copies of C mod 2. So another way is, I think it's a dangerous statement because, again, we haven't really checked that. I think there's a version we could also talk about L1 of S stat, of S plus stat and S minus stat. And I think there's something like a group which we could call L1 of kappa 2. So that's elements in kappa 2 which become standard after L1 localization. And so one way of thinking about this refinement is that we determine L1 of P plus.
Yeah.
And L1 of P plus is standard.
Okay.
Okay, so what remains is sort of this other thing, this C mod 8, this dies under L1 localization. And we do not control what happens to this C mod 8, or what happens inside this C mod 8. The hope is, well, it depends on, I mean, the Morava principle of maximal unhappiness probably sort of would require the C mod 8 to be involved, but the C mod 8 in some sense, or the C mod 8 cross C mod 2 cross C mod 2, that corresponds at the prime 3 to one of the 2 copies C mod 3, and at the prime 3 this was not involved. So in some sense this is related to the question, does I2 itself, which can also be decomposed in something Morava would call half of I2, and then there's a vibration between it, is I mean, how badly is that twisted up? No? I mean, that's a very vague statement, but I mean, that's something, I mean, that's sort of related to that.
Okay, thank you.
So
There is
Jack unmuted his phone. I don't know.
Yeah, Jack has written something in the chat. Can you have a look?
Oh, let's see. Yeah, there are things on the chat, I realized. Oh, so he says, wonderful. So it's a paper by Venkov, cohomology of groups of units in algebras with division. I have a vague memory.
It's a
Vague
global
memory
number theory result.
of this paper, but it's a long time ago. A long time ago that I looked at it.
I mention it just because it links to the arithmetic history of this kind of question.
The arithmetic history of which question?
The cohomology of these groups.
Oh, I see. Okay.
Okay, do we have any more questions for Hans-Werner?
Is there any new, I think people need, I think the sort of vanishing conjecture about the cohomology of these groups with cohomology in the Lubin-Tate ring is wonderful. It's in one of your earlier papers. And
That's
I just
the chromatic, well, we formulated it in the chromatic splitting conjecture.
yeah.
paper. Yeah, I mean, it would be very nice to know that. I mean, to have a conceptual reason for that, huh? Which would then perhaps have a chance to generalize to higher height. But it's, I mean, the cases we understand, we know it because we've calculated both sides. And one of the sides is very complicated to calculate.
It looks somehow, this is probably very naive, but sort of about classical theorems in complex geometry about the vanishing of cohomology with coefficients in positive line bundles. I don't know any geometry in the p-adic case that would lead to that.
Mm-hmm.
But there are theorems like that. I mean, Liouville's theorem is a theorem like that.
Which theorem?
Liouville about non-constant functions on the projective line.
Mm-hmm.
It's another such vanishing theorem for sections of some line bundle.
Mm-hmm.
I don't know any geometry, any p-adic.
Well, maybe I should try to speak to some of our geometers.
I had a conversation with Bobkova about it a while ago, but I have no real ideas.
Mm-hmm.
Thank you, Jack. Do we have any more questions for Hans-Werner, for the speaker? Hello, John. Yeah.
Oh.
Yeah, John, do you want to ask something? I saw that your mic got, what's the word, your audio got unmuted. Okay. Okay, if we don't have any other questions for the speaker, let's thank him again. And since his collaborator is also here, let's thank them both for this wonderful piece of work.
Yeah, thanks a lot.
Yeah, thank you all for coming. Next week, we have David Barnes from Queen's University, Belfast, I believe, unless I'm getting the weeks mixed up. So I hope to see you there. Bye-bye.
Okay. Bye-bye.